on.
It's good.
Just check that your microphone is the same.
Yeah.
Okay. And
Good.
do you want to put this lower somewhere?
Yeah, it should. Yeah,
Maybe.
really like this. Yeah.
Yep. Okay.
It's good.
Okay. Well, welcome. Day 4 of our summer school. Today we have more or less whole day. It's primarily on machine learning. Machine learning in R mainly. 2 parallel sessions. In this session, we'll have a talk by Patrick Schatz, who's been to our summer schools already. He also gave a talk about Ml3, but things changed since then. There are lots of improvements. So I think it's worth a new session. And just to say, Patrick is he's a consultant at a company called Syncra, based in Zurich, Switzerland. It's a data science company. It's a small consultancy, but also growing here. So congratulations on that. And doing a lot of interesting projects. And Patrick is also one of the developers in the core MLR group. MLR stands for Machine Learning in R. It's simple as it gets, right? Then there was a package MLR that I accidentally bumped on Patrick actually on Twitter, and I was using a super learner package made by colleagues from US, and then Patrick says, "Why don't you use our MLR?" I said, "What is MLR?" So then I looked at it, and I discovered that they're very active. And in the meantime, they as soon as they made a package that works, and they got the community, they decided to throw it all down the trash and start from the beginning. That's usually open source. And then they call it MLR3. There's a story why it's not called MLR2, right? And so you can say about that. But so they call it MLR3, but now it's a really very ambitious and community and project. And we're super happy to have Patrick here with us. And so please ask questions, and Patrick are going to talk more about the general design and how the software how software can be used multi-purpose. And then Leandro is going to do a second block where he's going to show how this package can be used with the real spatial data sets to do spatial prediction and classification, regression, etc. So please, Patrick, take the floor.
Thanks, Tom, for the nice introduction, and hello, everyone here in the room and also joining remotely. I'm Patrick. I'll be your host today for some hours, and we'll talk about machine learning, general machine learning with Ml3, and also spatial modeling with Ml3. And Tom already gave you some information, some introduction. I'll explain a bit more about Ml3 in general soon. But first, I want to give you an outline of what we are talking about in the first session today. So the first session is really a bit intro into machine learning with Ml3 in particular. So if you already know more or less a bit about machine learning and whatnot, you might as well be interested in the parallel session about explainable ML, and maybe then join the second part on spatial modeling, because in the first part, we won't tackle spatial modeling yet. Just that you're aware of what's being the content of the first block today. So here are some points we'll cover. And so each block will be split into 2 parts. There will be one presentation part that I'll be doing, and then we will have a hands-on part where you can use the code that's provided in the repository that I shared on Mtri, but it's also on the slides. You can just download it and install the dependencies, and hopefully then also join the hands-on part. Before we get started, like Tom already said, it's a bit background for myself. I'm a PhD candidate in geoinformatics still, so I handed in my dissertation recently, but I haven't defended it yet. Formerly, I was at the University of Jena and NU Munich in the geoinformatics department in Jena. And since 2 years, I'm a DevOps R consultant in Zurich, Switzerland at a company called Syncra. We do R consulting for all kind of projects there. In general, I contribute to quite some open source projects. I like Unix and R in particular. I do a lot for Git, which is an alternative to GitHub. And yeah, I'm part of the MLR core team since 2018, I think, more or less. And have been using MLR, or started using the old MLR in 2016 when my PhD started. And since then, I've been helping to get the project forward, and also contributed all the spatial parts that are in the package so far, together with a colleague of mine, Mark Becker. So we do this usually in a tandem. So shout out to him as well, because he's a very important person for the spatial part as well, and in general for the project. Here's a quick overview of the company I'm currently working at. So we are a small company in Switzerland, 10 to 15 people, doing everything in R, open source, focused, led by Christoph Sachs and Kirill Miller. You might know Kirill Miller. He's also very active in the R community. Tibble, dplyr, DBI, DM, that's some of his packages. We are a Studio certified partner, so we install and configure all our Studio products, Workbench, Connect, what else our Studio offers, and just what there is a need for the data science infrastructure at a certain institution. So if you're ever interested in such a work culture, feel free to approach us. We're always open to interesting people that are motivated to join us eventually. All right, so let's get started now with the content. So here's a quick overview of the structure again. So we are currently in block 1 here. Then there will be the second block about spatial modeling after the break. And depending on how the time is, Leandro will have 1 hour for the third block, in which he will present a use case example, which is quite advanced. So it's good to cover all the basics beforehand. And eventually we'll just be a bit shorter than 1 hour, but we just see how it goes. Depends a bit on how much I talk and how much time I take. Here you see the link to the resources, and also how you can, with this one comment, quickly download everything. There's a quote missing, I see at the end, so we should put that in. And then it should just open our Studio project for you with everything in there, including the slides that you can open in your local browser, the HTML. But it's mainly important for the use case and the hands-on part later on. We'll help you also installing all dependencies in case you have problems there, but everything should be also written down in the README, so it hopefully works out of the box with our end. All right, so now we'll start with the Ml3 overview. I'll talk a bit about machine learning building blocks, the essentials, and then we have a short break before we move to the hands-on tutorial, and then hopefully we make it in time for the first coffee break. All right, so let's get started. The MLR team. So MLR, so the old package without the 3 at the end, was originally created by Professor Bernd Bischel. He is currently a professor of the chair of statistical learning and data science at LMU Munich. And he created this package during his PhD back then. And back in the days, there was MLR, and then there was the old Carrot package from Max Kuhn. And these were the first attempts to harmonize modeling in R into a framework, and not just relying on single individual packages for different learner implementations and whatnot. And yeah, this package was around for quite some time, and it got better and better, but also bigger and bigger. And this was a problem in the end. So we had multiple thousand lines of code, I think 10 to 20,000 or so. Our tests were running for almost more than an hour back then on Travis CI back in the days, where things weren't yet parallelized and whatnot. And it was just at some point almost impossible to maintain, or very a big pain for the developers and the maintainers. So this led to the decision at some point that we need to do something, and this cannot continue like this. So the decision was made in 2017-18 that we need to split this big package into multiple smaller packages that are easier to maintain, that can be distributed among the developers better, and also include all the things we have learned on the way, and especially Bernd and Michel Lang, who's the main other developer besides Bernd, have learned on the way. So things they come across that, maybe this was not so good, maybe we can do this better, now this bites us, maybe we should do this different in the new version. So all of these ideas were put into the new Ml3. And also we thought about, is it still good that we rely on the S3 class system, or should we maybe look what other systems are available? And just shortly before, there was this new R6 class system coming out. It's really object-oriented, more object-oriented in effect than the old S3. And it had some attributes that very much help us and we could profit from in the modeling space. So it helps us to not always copy things around between objects inside the modeling phase, especially when you do resampling, have a lot of objects. But we use reference semantics, and by this we save a lot of memory, and we are way faster, and we can do things that we couldn't do before. So that's why Ml3 was born. It was announced in EUSR in Toulouse, 2019, very early. So it's now 3 years old, and right now I would say we are quite good and quite stable and close to 1.0 stable release. Currently sitting at version 0.14, at least the core. And yeah, the core team of the project is more or less 5 people. I mean, it depends a bit on how people have time and are involved. And I would say 5 to 10 people in general are actively contributing to the project. And of course, then there are single contributions from time to time from outside. Most people are to some sort associated with the LMU in Munich or the TU in Dortmund, where Michel Lang has been sitting. And these two are really the heads or the main scientific leads of the project. And yeah, so this is more or less an overview about the ecosystem, and to answer the question, maybe why Ml3 is called Ml3 and not Ml2 or something else. So the old MLR is sitting on the major version 2 point something. So that's why it's essentially version 2 of MLR already. So we thought, well, the next step is then the 3rd version. So that's why it was called Ml3. And that's where we are now. And yeah, so that's the story behind it. So MLR2 more or less refers essentially to the normal MLR without any number at the end. So these are the two packages available. And you can still use both, but if you start out new, I highly recommend using the new one, Ml3. Good. Here's an overview of the people behind it. So that was our workshop last year that we did in Corfu. You see all the people. Here's Bernd, here's Michel, the 2 main people. And here's Mark Becker, who also developed the spatial packages with me. And yeah, then some other people from the core team as well. Some are missing, but I think it's nice to put some faces to names at some point. So let's dive in. Why do you actually want to use Ml3? Usually, if you do machine learning, right, you want to train, you want to predict, you want to benchmark methods on data sets using different tuning methods or feature selection. And all of this usually, in the best case, using the same syntax. That means you don't want to switch between different syntax of various implementation and packages and notations and formula interfaces and other ways to pass the data and whatnot. And to make all of this consistent in R itself and to make everything available in the same way, these were the design principles of Ml3, and in general, not just of Ml3, but of every framework usually that tries to harmonize and unify things in any language. Here's again an outline of the problem that I just talked about. So usually in R, you have very different ways in all of the implementations of specific learners to specify what you want to do. You have here, for example, for the E1071 package that implements the support vector machine, or one implementation of the support vector machine, they use the formula annotation to specify what's your target, what is your data. Then here you use the data frame to pass your data, and you can use direct arguments for the parameters, for the cost, for example. Whereas if you would use an XGBoost, you use a very much different notation. For example, you use a vector for the target, you pass a matrix instead of a data frame, and the parameters are specified in the list. So, and I mean, while at some point if you're familiar with R, this is doable, of course, not a problem. Every time you use a new package, you would have to look up how they do it. No, before I can use this package, I have to convert between formats. This time I have to use a formula notation, this other time not. Why? What is the difference? Why do they all make it so complicated? And I mean, this is also something that some users really don't like. They want to have a specific centralized way of doing things, and I fully support that. And we try to do that. We try to harmonize things, take this pain away from users, and just make it one interface for all learners and methods that are available. So talking about R6, which I already introduced briefly, but it's not very widely spread in the R community, and it's a bit unusual also from the way it handles objects and methods. So I'll have this one slide for R6 in a nutshell that hopefully teaches you everything you need to know. Before I start, I want to mention that there are recent developments for a new class system called R7 that is being developed by multiple stakeholders in the R community, like the R Consortium, RStudio, and many others. They try to harmonize things in a way that they want to make it easier to use, like using R6, but also more powerful than using S3, which is the old and usual class system that many people use. And R7 should be something in between R6 and S3. So if all of that doesn't have any meaning to you, don't worry about it. You don't need it for modeling. It's just a bit of internals. But I just wanted to mention it that there are recent developments even making this easier. Yeah, Tom?
In R6, why is it called R6? I mean, it's not like R because it's R language or something.
Actually, I knew it, but I forgot it. So I guess a web search might help there easily. So objects are created using a constructor, and the constructor is the new method here. So, for example, if we create a new object task from a task class, we would use the new constructor and pass it some arguments. So it looks like a function, but it's actually a method, and it's the constructor method. So this creates the object in the first place. Then objects have fields that contain information about the object. For example, after we've created the object, we can query a row, and we get a value back, and it tells us how many rows this object in this case has. Of course, all of these fields and whatever the object has is predefined by the class when it has been created. Objects have methods, and methods are like functions, but are not functions. So they're really called methods, and that's the terminology to call them. Because there's all the difference to normal functions, but this doesn't really matter right now. So you can just call them like functions, but you always have to prefix them with your class. For example, here you have the object that we've created, and then we call the filter method. We can pass it some arguments. And the interesting thing is that if you do that, and that is actually something that should be different here. So they change the objects in place. So usually this one here should be a 10 now, because this should have been mutated, this one, but I guess the cache I was using on this chunk did something that was not so good.
So this in general starts a lot to look like Python, how you do things, right?
Yes, I mean, this general approach of object orientation, that you have a class that has methods, fields, active bindings, and other things, is not R specific. That's a general approach of defining objects in the programming world.
And is it many now developers in R switching to R6, or is it just,
we don't see many because people are not used to the class system. I think R6 is around for quite some time, but it's mainly used internally for packages. But we see, and we also do that people then write wrappers around and just expose functions that use R6 internally, but don't expose it to users. because we also got the feedback that people told us, it's nice that you do this and maybe it helps internally, but we don't get it. Like, it's too complicated.
There's a number of use cases for which it works better.
Exactly. So
which doesn't work better.
Yeah, but for users, it's a different concept, and usually R is introduced and taught in a different way, more like scripting and function-based and not relying on the R6 file system. You just have the S3 with the S3 dispatches that just does things in the background that looks like a function. And R6 is a bit like, you always have to use this constructor at the first, in the first place, constructor object, and then you have active bindings, methods, fields, and all of these different things. And they help, especially in what we do. But of course, it's a different approach how to do things. But that's in a nutshell. And remember that this should actually be a 10 here. So because we can mutate objects in place. So this is wrong at the bottom. So coming to machine learning in general. So usually here's a sketch of how machine learning building blocks look like. So on the left, we have our learner, our machine learning algorithm that can be of some type. We can have a classification learner, regression learner, cluster types, survival learner. So all of them do different things and have specific field-specific attributes that are important for the specific use case. Of course, the most important ones are classification and regression. That's what also you mainly deal with. And then on the other side, we have the optimizers for this learner. So we can do hyperparameter tuning, we can do feature selection, we can do pre-processing on the task, on the data in general. We can and we should do resampling to estimate the performance of our model. And this is more or less in a sketch how machine learning works on a very high level, right? So of course, there's way more to it, and we can go into details. And there are things I have left out here, but I usually like this sketch as an overview to get started, to get an idea of how things are. In MLR, so we want to find solutions and provide easy approaches for all of these building blocks. So in addition to these building blocks, we also focus on parallelization and error handling and encapsulation. So all the technical parts that usually users don't want to deal with and are happy that they just work if they use the framework. So the overall idea is that this topic of this slide, want to make benchmarking and using multiple methods, datasets, tuning algorithms easy. So of course, if you stick to one learner, one dataset and everything, maybe you can do it in 10 lines of code. But once it comes to extending all of these and setting up a matrix for benchmarking and for different methods, it gets complicated in many ways. And you will see later on how we approach benchmarking and how we can reduce the amount of code and input to a very few lines to efficiently create some benchmarking experiments in R. So now I've given you some introduction, and you might think, okay, is it all worth it what I'm doing here? So I'm sitting now here, and this guy is talking about some framework and here and there, and I've maybe done something else with some normal random forest package in R, and it worked great, and is it actually worth it? I won't comment much on the slide, but in the end, it's you that decides if you want to do that or not. So you can react like this, or you can react differently. It's up to you. Everybody goes their own way. And I also not saying that Ml3 is the best framework that's out there, right? So there are other frameworks as well, and maybe they suit you better in a different way. But at least keep it on the radar and try it out maybe once. Besides the beauty of building everything in a normal syntax, in a centralized syntax, and making it easier to read and to execute, you also have the benefit that, of course, we in the framework and developers, we test things, and we test things quite a bit. So across the framework, I think we have almost close to 10,000 test scales in all packages combined. Of course, we might still miss some parts, but of course, I guess this is not a hot take that we have more tests than most of the single developers that would maybe code their cross-validation on their own. So you can most likely be sure that if things are running, they are accurate, at least the outcome, because we have tested this quite often. And we try to make or include sensible defaults for specific building blocks, being it learners, being it tuning strategies. We provide tuning spaces, so you don't have necessarily to put in your own tuning spaces if you're lost on how to tune an XJBoost, for example. We also provide you some guidance there with some references about the tuning spaces and whatnot. So I'd say you can reduce your potential mistakes, rely on some nice defaults, at least to get started, and then explore more. Yeah, so here is some code that shows you how we can do a full benchmark in just 20 lines of code. I walk you through and we'll see how it goes. So at the top, we load the Ml3 reverse, which is a wrapper package. A wrapper package like the tidyverse, more or less, that just loads some bunch of Ml3 packages. We set some, so internally we use the logger package, LGR, to do some logging modifications, so to reduce or increase the logging verbosity. I set it here to warn, otherwise we would have quite some output here that we don't want to see here right now. Then we set a seed for reproducibility. We get started, we load some example tasks that we include into the package. Two in this case, we load some learners, and you already see how we do that with these sugar functions here. I will come to them later. Here we use the RPark learner and the Ranger learner. So some tree-based learners. And then we use the benchmark grid function. We say, okay, we want to use these tasks. We want to apply these learners, and we want to do some resampling. And here we just say we want to do CV, which is cross-validation. And then we say, okay, let's go. Execute. And then we say, okay, how did that go? So we do some autoplot, and autoplot is generic ggplot and ggplot2. S3 generic for this object class here. Then we say, okay, let's evaluate this using the classification error measure. And then this is what we get. So we see a box plot faceted by the task that we use, and we see how each learner did in this classification, in this resampling. So this is, in a nutshell, how you do a benchmark. Of course, there's quite some stuff missing, right? We didn't do any proper tuning here. We didn't do some pre-processing. We didn't do feature selection. And we didn't do any post-hoc analysis of trying to interpret the models or whatnot. But the syntax is quite clear. We load the learners, we create the tasks, we put them into a grid. We say, okay, let's go. We could potentially parallelize it here, but we come to that later. And then we visualize the results. So we can probably almost skip this slide because I've talked about the reference semantics already quite a bit. But in general, this is how an object usually in R6 looks like. So you have an inheritance. You have one object at the top that is inherited by some others. So these are all their own object classes. So for example, we start with the learner class. Then we have learner classif and learner regression task. And then we have the specific learners. For example, the RPark classif learner that inherits from both of these. And they inherit all the fields, all the methods from the parent classes. And by this, we have reference pointers, and we just don't copy things around all the time. So we don't have everything duplicated in memory, and we can just make pointers, and that's way more efficient. Internally, we use data table to do all the operations, which is way faster than just using plain data frames in that case. That also gives us some speed and a lower memory footprint. And we use the future package for parallelization and the logger package for logging, and some other internal helpers like backports and checkmate for checking and making assertions. Yeah, Tom?
You mentioned these sugar functions. Why is it called sugar functions?
It's syntactic sugar. That means that these are functions that actually do the same as if you would do like the raw R6 notation. You would create an R6 object and then do some stuff. So they just wrap all of these in a very short manner. So you don't have to type that many characters, right? You don't have to type class name, $new, and then parameters. But for example, you just type LNR, that stands for learners. And this is the same as if you would create a task class with $new learner, for example.
And these sugar functions come also with help documentation.
Yes.
See how you use them and everything.
Yeah, and then you have reference semantics to the actual objects classes. So exactly. So they are just.
And can you, before you like what you show this workflow, it's like it's basically you broke it into the minimum possible pieces, right? So you don't want the simplicity is always the best, right? But for example, if you before you start doing the benchmark, could you estimate how much time will it take? Because it could take 10 hours, it can take 3 minutes.
I don't think you can estimate that in general, because that depends on your data size and the learners, how efficient they are, and eventually the tuning you put in. So you can't really estimate that. But of course, you can run a very small example and just check how long does that take, and maybe eventually just predict how long it will take if you scale it up to your whole data.
You get the progress when you run something.
I'll come to that, so we can some progress. But of course, this estimate is not linear, and sometimes it just doesn't work out right, because the more data you have, sometimes you have a logarithmic increase in time or something, because your learning just takes way longer or so. But I'll come to the progress later, and we see how you can see the progress there. So here's an overview about the whole ecosystem of packages we have. So in the center, there's the Ml3 core, and we've broken it down into some categories. All the green ones are stable and on CRAN. All the orange ones are in development and at least on GitHub. We will later on also focus on the spatial part, which is located down here in the so-called special task and targets category, especially Ml3 spatial, Ml3 spatial temps-to-be. There is also Ml3 temporal, but this has not seen that much development yet. But it gives you a nice overview of how big the ecosystem is. And remember, we do this also free in our spare time with like 5 to 10 people. And some of these packages are fairly advanced. So I'm always impressed if I look at this myself, what the team has accomplished over the years. So building blocks. Learner task on the left, which define the meta operations, and then on the right, the apply part, where we do all the things, pre-processing, tuning, feature selection, whatnot. If we come to the general modeling approach, and this is an important slide because I like to split these into these two blocks. So in general, if you do modeling, you usually have these two approaches. So you have I call it train, tune, and predict approach. That means you train a model on all of your data points. You predict to some new data, of course, without the response. So you don't know the performance, you just do a prediction. And for this, you use the train and the predict methods here. And then what you get out is like your final quote unquote model that has been tuned on your data that you have available, and some predictions on some new data you've made. So usually that's what you want in the end. You want your prediction. You want some information in an area where you didn't know how things are, and you predict it, you train a model and you predict it there. So this is one thing. But the problem here is that you still don't know how good you are, how good your model was. So you just got some numbers. It can be meaningful, they can be meaningless, you don't know. I mean, they can be the truth or close to the truth, but you don't know. So you just need a way to estimate how good you were. And this is the second part of the whole thing. So the performance evaluation. So how do you actually, so the whole part is designated to getting to know how good your model actually is, or estimating how good it is. So what do? You split your initial data into train test. You use a resampling method. You resample quite often, and you use a lot of iterations because you want to reduce variance among those iterations. Of course, you tune your model the same way as you would do it on the left side. Because every train and predict step needs to have a model that is being tuned on the data at hand. And then eventually, if you don't want to just rely on one model because you don't know which model is actually the best for the job, it might have worked in the past, but the new data is maybe different, so maybe another model might be the better choice. You benchmark multiple models. So you want to see how good is model A, B, C, D, whatever you use. So you benchmark them, and there you get some performance estimates, because in the test data that you use here, that you split, you have actually the truth of your response. So you can compare your model predictions against the actual values that you have, and you see how good is actually my model that I fitted here. How far off is it from the actual truth? And based on this, you then say, you do the left part, and you say, based on the performance evaluation, my model is as good as that, more or less, because I've done this and that X amount of times, and I'm somewhat sure that this is how good I am. So these are the two blocks that you usually do in machine learning, or in general, not just in machine learning, in statistical learning. So this is not any difference here. And the right part here, where you do the performance estimation, you usually use nested resampling to do that. And here's a nice overview from one of my papers 2 years ago, where I tried to break down what actually happens in nested resampling, both on the spatial and on the non-spatial side. So let's focus maybe first on the non-spatial side, because that's usually what everybody does if they're doing a normal cross-validation, not focusing on any spatial parts. So you have the outer loop here, the blue one, and you have the inner loop. The outer one is really for the performance estimation. So that's where we crunch the numbers to, in the end, say, this is how good our model were. And in the inner one, we tune our hyperparameters for the models in the outer loop. So if we do this in more detail, what we see here is that we have train and test. So the purple ones are training, the yellow ones are test. And what we do is that for each fold, we take the train set, we only take the train points, and we split them again in train and test in the inner loop. So we leave out the yellow points at the top, so they have never been seen by the model. We put them only the train points in the inner loop. We again do a split in like 5 folds or 10 folds. And here we test different hyperparameter combinations. So we just want to get to know what kind of hyperparameters are the best ones that generalize best with our model. And here we set a strategy for the tuning. We tell the model how long it should optimize itself. And then we take the best hyperparameter setting from the inner loop, apply it on the training, on the model that is being fit on the training points in the outer loop. And this model is then does a prediction of the test set. And because we know the target values of the test set, we get an error value from our measure that we've selected. And we get this for each fold and probably for multiple iterations. So you can, for example, say, we have 5 measures in the outside. We do this like 100 times. So we get 500 values on the outer one. And this is in the end our performance estimation. We can average that, we can take the mean value, whatnot. But each model that has been tested and trained on the outer one has been optimized first in the inner fold. So this is a 2-layer nested resampling approach that you usually do to have a proper and, in the best case, unbiased performance estimation. And maybe it's even more easier to understand in the spatial part, because there you see how we can use the train points. You can see that we use only these then in the inner loop, and then we split them again in train and test. It's maybe not so scattered as in the non-spatial part. So this is usually how you can think of the nested resampling if you would have to visualize it. And of course, all the code that does this, right? The splitting, making sure that you create the folds, making sure you run the inner tuning, making sure by the framework. I mean, you could code this yourself. And I think just a few days ago, I've seen some people on Twitter talking about how do you do actually cross-validation nested resampling? And I think, I'm not sure, maybe it was biased, but most of the responses were, I'll just do it myself, like I can do this, I'm that cool. Of course you can do this and it's cool, but you can also make mistakes by coding this. and it's easy to make mistakes and not realizing them because you always get some value out. So, but you're never sure if it's right? So I'd rather rely on something that has been looked over by multiple people. So essential functions of Ml3. You've partly seen them already. These are the sugar functions that save you from typing R6. So you can use TSK for task here, LRN for learner, MSR for measure, RSMP for resampling, and TNR for tuners to create the respective objects. And if you append an S, you can actually create multiple ones. There's a reason why we don't vectorize the first one, but I'm not going into detail now. So these are the ones you usually use to create your full pipeline if you set it up. If you call these without arguments, like they are here, you see actually what we have in the tin in our framework. So they just print out all the available respective objects that you can create that are implemented. So, for example, if you call LRN, you get a dictionary of the learners. This is how usually it looks like then. Of course, I modified this a bit here so that the output looks a bit nicer. Usually, you can also just use learners per se without all the subsetting I'm doing here. But if you do that, you see all the learners we have implemented here. It stops at 117. But we could also, I'm not sure if this already includes all the extra learners we have in the extra learners package, because actually the Ml3 learners package only provides a selected subset of learners that we know people like to use often, work well, are battle tested, so to say, and all the other ones, niche learners for some fields, are usually then implemented in the extra learners package. Yeah, so this just to give you some glimpse how it looks like.
And there's an online description of all the learners.
Of course. Every learner has their help page.
The MLR has a very nice tables with all the parameters you can change. Is there also an MLR3 like that? Or?
Yes, there's one. You'll find it surely here, but also on the Kageshon page of the learners package, I think, and it shows every learner parameters and whatnot. And for some of these learners, we've also made some opinionated changes to the defaults. Sometimes for parallelization reasons, sometimes for other reasons. For example, for the random forest, we have implemented an additional parameter called Mtri Ratio, which is needed. So it scales between 0 and 1. It always picks a percentage of the features rather than an absolute number, because if you would use the normal Mtri during feature selection or whatnot, and you have less features that your Mtri actually searches for, your learner breaks. And this is usually a pain if you're trying to optimize random forest. But details. So we just want to give you an idea of that we try to tackle the details when it comes to certain learners and issues. Essential functions and methods. So all the functions listed here with the prefix with the dollar are actually methods from the R6 classes, and you need to call them like this. So you need to call them like class dollar method, whereas resample, benchmark, and these are normal functions, right, that you can call them. So you have the training method predict, and there's the predict new data. So predict actually without the new data means you predict on a subpart of your task, which is sometimes what you want, but often enough you have your new data in a completely different object and not within your task, right? Because you want to do predictions to a new data that is not within your training points. So that's why you would use predict new data for. Then you have resample benchmark, which are more or less doing the same thing. Resample, possibly using nested cross-validation, a single learner, that is what resample is for, or multiple learners and tasks, then you use benchmark. If you have started out using resample and have created a resample result, and you think, now I have this one thing, it took me quite some time, but I actually want to do multiple learners, multiple tasks. How do I have to do it again? You don't have to. You can convert a resample result into a benchmark result and just merge them. So there's no need for rerunning things and wasting resources multiple times. And then there's the autoplot to visualize things at the very end. We don't have autoplot for all the objects in Ml3, but for most of them. And you have arguments to change certain aesthetics and things. And of course, it's a ggplot that comes out in the end, so you're free to modify in any way how your object looks like. All right, so beyond simple data. Let's have a look at the time. Well, that's good. So what I've shown so far was often very simple data, right? Classification, regression tasks, a normal target, normal numeric features, whatnot, no spatial data information in the data, no spatial information in the data. But usually the truth looks a bit different, right? We have different types of data, from cluster to functional to ordinal to spatial, survival, temporal. There might be even more. All of these need to be treated different because otherwise you don't get unbiased results. For all of these, we have specific either learners or resampling methods or other ways to account for them or measures. But that's not all, right? So what about GPU training, multiple targets, and so on? It gets a bit advanced there. I won't talk about this, but most of this is also covered in the framework, either with extension packages or GPU-based frameworks like Keras or Torch that you can use. We have connectors for this. Some are early, some are a bit in better progress and maintenance already. But the goal is that you usually should be able to attach and use all of those functionality methods in the framework. If there's something missing and you would like to do something, please tell us, because the more requests we get, the more need we see to push on this front. Yeah, and this is, again, the slide I showed already before. Parts of what I just showed is tackled in the special tasks part down here. So you see we have the cluster package, Proba for survival analysis, then spatial packages, multi-output, functional data analysis, the FDA package, but there are still quite some missing, right? But we'll try to improve. So now that we've covered all the basics and intro parts, maybe let's go to a topic that sits between the basic part and the advanced part. Parallelization and ensemble models. So usually running a learner on a small data set, on maybe just one learner on one task, takes a few seconds, right? It's easy. If you put in tuning, it already takes a bit longer, depending on how long you tune and how big your data is. And then the first thought might appear, okay, can we speed this up? How can I make this happen, that this finishes within my next coffee, and then I can get back to my computer and things are done? Well, sometimes it works, sometimes it's not so easy, but parallelization is definitely something that tries to help you. So the same goes for ensemble models. So at some point you might think, now I've tested this one model on my data, I've tested this other model, and they're all side by side, right? But what if you would combine these models and their predictions to maybe form another model on top of all of them, called an ensemble, so to say, that includes all of the information, predictions, and what has been done beforehand, and just operates on this and creates predictions again, but including all of this information. This is the idea of fusioning models in general and ensembles. This can lead often to better predictions, sometimes just slightly, but it also heavily complicates, of course, your modeling setup, right? And your interpretation afterwards, because you're mixing things together. You need to account for it. You need to fit multiple models and then another one on top. So it always has pros and cons. So there's no free lunch, so to say. But for parallelization in general, we use Future, which is one of the parallelization frameworks, and in my opinion, the best parallelization framework in R by Henrik Bengtsson. And for ensembles, we rely on the Ml3 Pipelines packages via so-called graphs or graph learners. So we just don't create a single learner. We create a graph learner that is composed possibly out of multiple learners and pre-processing steps, and then use a stacking or bagging to combine all of these. So let's look at parallelization and see how that works. On the left, you see some sequential code and some example here. And the big part that we need to look at here is that we just need this one line to say whether we want to run sequentially or in parallel. This is being made available by the Future package. So we say here on the left, we want to run sequential. We would not even have to specify this because this is the default. And here on the right, we would say we want to use the multi-session plan, which runs in parallel. How many cores and workers do we want to use? In this case, 2. And then we do the same thing. And you see the time difference at the end. We saved some time. So now you might think, hey, we used like 2 workers instead of 1. But like if I look at the time here, it's 27 seconds, and here it's 18 seconds. So that's like not exactly half. And yeah, that's usually the problem when you use parallelization, that you have some overhead. So what you do and what is happening is that the parallelization approach splits your tasks into multiple parts, in this case 2, and then at the end needs to bind them together again. And this costs time. And what also costs time is spinning up multiple workers in the first place. So every tuning strategy does this a bit different. The multi-session one here is relying on the socket-based cluster approach in R, a piece of cluster which actually takes some time. It got better in R4, but it takes some time. And this is in the end, if you sum it all up, the time overhead that prevents you from exactly having half of the time used compared to the sequential execution. Of course, if you run longer with more cores, this difference won't matter that much anymore. So parallelization is usually always encouraged. But also remember that it takes more resources on your machine or wherever you run it. And things might become slow in general, and everything heats up a bit and whatnot. So it's always a question you have to answer yourself when you're used. Usually, of course, in production, when you do your final model, for just a bit of testing, you're good to turn it off. So here are the takeaways I already mentioned. One important thing I haven't yet mentioned is that in Ml3, to avoid conflicts with learners that sometimes try to do an automatic internal parallelization of what they do, if it's possible, we turn that off and we rely on the internal parallelization of Ml3 with Future, which is often more efficient and at least better controllable than what has happening in the learner. That is important to know because, for example, learners like Wren and Forrest usually try to parallelize things in multiple ways. And if we would also apply some parallelization on top, you would have a multiple nested parallelization. And that usually is not something that is going to work, or at least going to cause problems on some ends. So keep that in mind. If you want to go parallel in Ml3, turn it on and off explicitly with Future. Yes, Leandro?
Yeah, but for example, you mean that if you just use one thread to bring like the whole forest of a random forest, it's better like just use one thread to do it. Actually, that's the question. Because when you like inhibit the parallelization of the ranger packet, for example, it's so how the Ml3 will manage it.
Well, we don't interfere with what the learner does. So yes, if you run sequentially in Ml3 and you turn it off in the ranger package, of course, it will be slower than the default. Then if you choose this strategy, you can turn it on manually yourself. So nothing prevents you from doing that.
Yeah,
But
we are doing it, by the way.
Exactly so. But if you, I mean, you can also try to turn it on and use Ml3 parallelization. There's nothing preventing you directly from doing that. In some cases, it works. But we've just seen that there are possibly conflicts and troubles and issues. And if it comes to that, it's hard to understand why that happens in the first place. So we just put this as a guardrail to users to be more or less safe.
Yeah, one thing that we noticed is actually it's way slow for the predictions. So because, for example, for random forest, if you don't set like manually, use more threads, even so maybe we in our side we are doing like we are not using like the Ml3 to do the prioritization the proper way in the prediction, but we notice that it's slow if we don't set it by manual.
Yeah, sure. I mean, you're free to just experiment. Also, what is maybe the fastest way? It really depends on the learner as well. So some parallelize efficiently, some don't do it. It's hard to give a general answer to that, but it's just important to know this in the first place, because if you know this, then you know I have to turn it on because it's turned off, like at least the learner parallelization, and the same goes for the Ml3 parallelization in general. So by default, you run sequentially at one core, whatever you do. And if you want to go nuts, you need to say so. Encapsulation. This is actually one thing that is new in the new version of Ml3 that hasn't been available in the old one, and that actually is big when it comes to production use cases. So you can use encapsulation for specific learner calls using the call R package, using an external process to execute certain learner calls. That means if a learner crashes, seg faults, whatever, sometimes for an unknown reason, sometimes just random, it won't tear down your whole experiment or session. So it won't affect everything else. And this has happened differently in the past. In the old one, and this is usually a pain, and maybe this is some part that also Tom is looking forward that it's not possible. And you can capture the logs even, you can look at the warnings of this specific encapsulated learner, and you can even have specific fallbacks for predictions maybe created to fill that up, or use a fallback learner to replace the one that has failed. So this is all very technical, more in detail described in the Ml3 book, but something to be aware of. I'm not sure how other frameworks currently do that, if that's even possible. It was not so easy for us as a team to do that, but yeah, it really can save your day, so to say, sometimes for large tuning experiments. Progress bars. Yes, there is progress. There hasn't been progress in the old framework, but in the new one there is. And we didn't do this ourselves, but we rely on the Progress R package, which again is from Hendrik Bengtsson, the author of the Parallelization Future package. And here's a small example how that looks like. The only thing you need to do is to wrap your code in the end, in this case, the executor of the benchmark, in the with progress function. And before, you need to set your handlers so that it knows how to output your progress. And here's a short GIF at the bottom that shows you how this goes. It can also show you some time estimates, if I'm not mistaken, based on the first iterations that have finished. And I think it just does a linear scale-up prediction of how long things will take, which sometimes works, sometimes not. But it's a nice way to see where you stand. And you cannot just print this to the console. You can also have some other outputs to a text file or something else. So everything is supported via this Progress R package. And this applies to the benchmark function, to the tune functions, as far as I know. Resample is the same as benchmark. And I think there's not even more that there is need for progress. So yeah, what you see here is repeated cross-validation with 3 folds and 50 times repeated. And because we use a very small data set and the R learner, this doesn't take long, but it's a nice showcase for the Progress R implementation. Yep, so model optimization is composed out of 2 parts. You have the tuning, for the hyperparameters of your model, and you want to optimize potentially your features and reduce your model complexity and the feature count. So these two parts are usually standing side by side and cannot be combined in one step, even though there is possibility to use filters instead of wrappers for feature selection, which you can fusion with the tuning step. Just some remark on that. But otherwise, you would have to run one after the other, and you usually have two optimization layers, which takes more time than just one. But the one you should always do, no matter the model and no matter what you do, is tuning. I mean, you can always add feature selection on top, but you should always optimize, in any case, your hyperparameters, even with a small tuning budget, just maybe. But don't just use the defaults. And for some models, the defaults are even meaningless. For example, for an SVM, like support vector machine, you have to tune it. There's no matter what. There are no meaningful defaults. The tuning space, and when it comes to tuning in general, you have the tuning space, the method, and the budget. So that means you need to select the range of your hyperparameters that you want to optimize within. You want to specify the method. So how do you do that? There are different, very advanced methods to optimize this, starting from very basic ones like grid search and design points. That is, for example, means you handpick the hyperparameters that you want to train by yourself. Grid search is that you define a grid of hyperparameters also by yourself. Random search is a bit more advanced. You just do a random selection within your tuning space. But I would still say they're all in the basic class. And then there are more advanced tuning methods, like you see mentioned below, like iRace, nonlinear optimization, generic, what is genus A? I forgot the name. Anyhow, you can look them up if in the tuning space dictionary. And if you print that on the left here, you see what methods we have supported. And there are also additional ones. For example, Ml3 MVO implements model-based optimization. That's an extension package again. So when it comes to tuning, we really have quite some options available because there's also quite some focus in the research group of Bernd in Munich to test and develop and try out new tuning methods. So I think we have quite some good and advanced and niche methods in there that are not available in other frameworks. Right. So in general, there are two approaches to the tuning, and this partly relates to the first slide I did with the train, tune, predict on the left, if you remember, and the resampling on the right. So you can do a standalone tuning via the tune function and use a task and a learner and a basic tuning strategy. That's usually what you do if you do your final predictions and you fit your model on the whole task. But you can also do it a bit different and create a so-called auto-tuner. What is an auto-tuner? An auto-tuner is essentially a learner that knows how to tune itself. So, of course, you have to specify this to some degree beforehand. But you can treat this auto-tuner once created like a normal learner. But the difference is that a normal learner just doesn't know how to optimize itself. It has no parameter space, it has no tuning budget, whatever. Whereas an auto-tuner has all of this information. And once the auto-tuner kicks off, once you say, auto-tuner, go, train on this data, the auto-tuner optimizes itself on the data first, and then you have the result. So this is usually what you want to do in a benchmark or nested resampling case, because there you just do all of this in multiple layers and stages. And in every stage, you just pass this auto-tuner that knows how to optimize itself on the given resampling. And this just happens then without any further manual inputs of yours. And this auto-tuner, how can you create it? So that's how it looks like. You give it a method, a resampling method, a tuning method. You say, for example, you should want to terminate the tuning after 4 evaluations. Of course, the auto-tuner relies on a normal learner in the first place, so you need to tell it. And here you need to specify which parameters to tune. So for example, here, this parameter, we give it a range here for the tuning space. We say, okay, we want to do this on a log scale. And this is then creates all of this, creates the auto-tuner. You say auto-tuner train, just train on this task. And then the auto-tuner trains itself. And what you get back is an auto-tuner that you see has been trained. It contains the learner information. It contains the search space that has been optimized on, and so forth. So trafo set means we have set here a trafo because we have used a trafo to transformize the tuning search space. And this is, in a nutshell, what an auto-tuner does. It's more or less the same as if you would specify all of the things manually, but this way you just have a single object that is able to tune itself. Ensemble models, I've touched them before briefly, and yeah.
Do you trust the auto-tuner? Do you think it's a good way to go?
Why shouldn't it be?
Well, I mean, every data set is a bit different, every problem is a bit different. So it creates an illusion to people that they can simplify their problems, I guess.
Maybe, okay, I try to specify that a bit more. What you put in, you're under control, how you create the auto-tuner. You define the tuning space, you define the resampling, you define everything. It's the same as if you would do this so-called manually, I would say, step by step without using one object. And in the end, all of this configuration and the task, you say, you define this. So in the end, it's the same as if you would do a normal tuning of this learner with these specifications on this task. So there is no difference in doing this without an auto-tuner or with an auto-tuner. It's just that this is everything a bit more wrapped into one object. It's a bit easier to handle, and you don't have all the single parts floating around. But because usually, right, you have this tuner somewhere floating around as an object, you have the resampling object floating around in your code, in your environment. And this way, you just have one object. You can modify, change, and you should, in fact, of course, do so. And you should, of course, also use different tuning spaces here, maybe, to estimate the performance of the model. Essentially, this is not doing any magic. This is the same as if you would do it with your bare specifications of how you want to tune a model. So this is really important to get here. This is not some, I know there's the word auto in the name, and it's, well, we had it because it's essentially an object that tunes the learner automatically, right? That's the idea of it. But you are in control. Okay, ensemble models. I briefly talked about this at the beginning, next to parallelization, but now let's have a bit more overview. There are different ensemble types of how you can combine ensemble models, like multiple models when you do a prediction. There's bagging, there's model stacking, and there's multi-level stacking. So what are the differences? When you use bagging, you basically, this is an averaging approach, or in the case of classification, a majority vote. So that means if you have 3 learners, right, that you want to combine, and you predict all of these 3 learners on the task, every learner comes up with a different result for that specific class on that specific point. So what happens if you use these 3 learners? And of course, it's nice to have an uneven number here because you have a clear result, and that's usually also something you should do, because otherwise you have one learner that says, this class is 3, and the other class, and then for the other learner, the prediction is urban or something, right? And then you say, well, what is it now? Like, but if you have 3 learners, then you have a majority vote, and usually then you find a good solution. But of course, it can still be that all of the 3 learners predict something completely different, then you have again the same problem. So it's a bit easier for regression because they just have numerics, and you can, for example, use averaging and just take the mean. But just as an overview, not going into further details here. Model stacking is a bit different. So what model stacking does is that for all of your base learners, so to say, you use the predictions for these models and you use them as features for your subsequent Ensemble superlearner. So these predictions are being taken as new features for the new training step on top. This is what stacking does. In multi-level, stacking is, well, just combining multiple levels of either backing or stacking, and doing this just, making this even bigger. So of course you can do the stacking on multiple levels and use the predictions from multiple levels and layers, layer 1, 2, 3, 4, and at some point you stop. But of course, it depends on your budget and how long your tunings and your model fittings take, right? At some point, there is a limit to that, but if you're running on an HPC, you might be good and you might have a lot of budget and you just build a lot of models. It's up to you. All of this is supported via Ml3 pipelines. And this is how the syntax looks like. You define so-called graph learner here. And here you use the pipe ops, we call them. The pipe ops are bound together by this custom pipe operator here. Note that we have one bigger than sign in the middle than the normal pipe operator. And what is happening here that we use two learners here, linear model and SVM. We say, okay, we want to have a learner cross-validation here used on those. And this is just combining them together and just splitting them in the first place. And this is binding them together in the end, so you can discard this one. And then on top, we have our super learner, our ensemble learner that takes both of these inputs. And this is, in this case, a ranger learner. And this is how it would look like in a diagram form. So you have the training data, we have our linear model, our SVM. This is actually doing nothing, just having to control all of these. We do a feature union in the end using this pipe up here, and then we train a random forest based on the base learners. With the graph stack we've created here. So a graph stack is actually a graph object, then you can, maybe if you run that, you see that. But it also has a train function and you can train it again on a learner. But of course, what we didn't do here is any tuning, right? We didn't do any tuning, any optimization. This is just a baby example of how you do it, just to give you an idea also with the diagram how this looks like.
So this is just to build an ensemble?
Yeah.
Without preparing all these learners, but you could do them separately and then just pass the parameters. So
yeah, in the end, what you need to do is to build this graph stack and to trigger this at the end. Because the graph stack here, this is just like a meter object that has all the information of how this pipeline is being triggered. There could be multiple steps in this pipeline. You could do some pre-processing here. You could do some tuning here. Then you do the feature union. And I mean, at the end, of course, you also want to tune your ranger usually. But this is just a very simple example of using defaults. You shouldn't use this in practice, of course, but just to get the idea going. But you see how we can do this in 11 lines of code. Or, I mean, if I remove the comments, even less. And there is so much happening in these few lines of code here. I always find this incredible if I look at this. So. Workflow and execution, and we have 50 minutes left, and maybe let's see if I can get at least some hands-on part to get going. But this is we're almost done. So workflow and execution. So how do we actually structure and execute your code? You can use essentially 3 different approaches. The first one is you script everything in subsequent steps. That's how you usually do it in R, right? You start with your library calls, you script everything, you create your learners, you create your tasks, you tune, you do whatever. Fairly fine to do that, completely fine, no issues about that. That's one way to do it. But there are others that might help you, especially with workflow and reproducibility. And one of these is to use Ml3 pipelines, partly as I've shown you before, to create a so-called graph learner that has all of the representation of the steps within one object. And if you trigger that one object, this will completely execute all of these steps. Of course, it still requires you to script that in the first place, but such a graph learner can be very powerful, and you can sometimes just execute certain branches of that. So for example, you don't need to trigger all of the pipeline in the first place. You can just say, oh, please just go the route of this learner at the bottom, right, of one of those 3 base learners, and just do this first, and then trigger the other ones or something like this.
And this name graph learner, I mean, like, for example, I'm not interested in seeing the graph, right? I'm just interested in running the model.
Yeah.
But it's called graph, and that kind of confuses me because it's kind of expectation that you.
This is a graph class.
Yeah, you use it to plot, right? So, but you actually, it's called graph, but you don't have to plot it. It's just how you organize it.
Right. The graph learner has a plot function that gives you a representation of the graph, how it looks like. That's why it is, well, in general called a graph learner. And a graph, we know that this term is debatable.
Like I think what they wanted to say is the workflow, right?
Yeah.
The workflow.
The workflow you can get out of this in various ways using the plot function of the graph learner. And what you need to think of a graph learner is just, it's a representation of your complete workflow from the start to the end,
Yes,
including pre-processing everything.
I understand. But when I see the word graph, I mean,
What do you think about when you?
I think about plotting. I think about.
Okay, yeah. Well, yeah, it's a hybrid in this case. You can plot the graph, but you can also execute the graph.
Okay.
Yeah. And the third option is you can use external workflow packages like targets or break, which is usually my favorite. They're very powerful. You can combine everything together and also rely on caching and parallelization, and it makes sure you don't rerun things twice and you don't forget certain things of your overall pipeline. And there's in fact the Ml3 targets repo where it shows you how to use Ml3 and targets. There's a pending blog post of myself showcasing this in more detail, but you can already have a look at the repo, maybe figure it out yourself. So these are the 3 ways to trigger your pipeline. And there is a typo. That should be an S, of course. Was that all? Is that everything, or is there something missing? What didn't we cover yet? We didn't talk about data preprocessing, proper error handling, database backends, survival learners, feature selection, geospatial methods, upcoming in the next block, model interpretation, which has been covered in the parallel session here, which is also, we have integrations for Daleks and for IML packages. And probably something I forgot. So machine learning is big. You can do a lot of things. You're free to do a lot of things, but of course you can also, you don't need to do everything, right? That's also maybe one point I want to mention. Focus on the things you want to do that make sense and that you want to get out as a result. Don't try to cover the whole space. There are reasons to do everything, but you will get there. Don't do everything at once. Try to understand what you do. Try to understand, does it make sense what you do? Are the results meaningful? And is there actually maybe some parts that might bias my results? That's very important. More resources in the Ml3 book and the Ml3 gallery, where we have like 40 use case posts of how to tackle certain specific use cases for all kinds of problems. Here's an overview of the resources. We also have a MetaMost channel that you can join, or you can use the Ml3 tag on Stack Overflow. We try to be responsive, but please bear with us if we either overlook the post or something else. You're always welcome to ping us in MetaMost and something else. We also have some cheat sheets. And here's again an overview of where we are right now. So we've covered this. There's now a bit time left for the hands-on tutorial, but not much. And then in the second part, I'll reconsider if I continue first with the rest of the hands-on tutorial or directly skip it and move to the spatial part. In block 2, we talk about the spatial extensions. I also have a hands-on tutorial. And then in block 3, there's a use case example from Leandro. So, and yeah, with that, the first part of the presentation is concluded, and we can now go to the hands-on part. Before I do that, of course, I ask for questions. I also see one Q&A, but I'm not sure if you want to do that now or what is the...
No, it's a good moment, yeah.
Yeah, so what is the question? What about model deployment? Is there a lightweight version of the package which can be used for production level? which only includes parts needed for inference. A lightweight version of the package that can be used for production level. Not sure I fully understand the question. What do you mean by lightweight version for production level? Because everything we have here in the basics are in the core package, and you need the extension packages to deploy or to create a model in the first place. And I'm also not sure what you mean by model deployment. Do you mean just uploading it to a certain online database for comparing it to others? Or so there's the OML, Open Machine Learning connector that we have, Ml3 OpenML. That might be helpful for this, also for getting data sets. But other than that, I think we are not as advanced as maybe scikit-learn or others in terms of MLOps and all of these new developments recently, but we try to get there. Maybe this is an answer partly to that. And yeah, maybe I can answer that, or you can refine the question a bit. Yeah.
I don't see why you wouldn't be able to deploy this. So.
Yeah, so I mean, the term deployment is also a big term, right? It's not always clear what you mean by this, but all right. So I say, so there was this one Q&A. Then before I jump here, let's do this here first, right? Are there any questions from the audience on this first block?
This code you're running is on GitHub.
Yes. Yeah.
How does the MLR package compare with Tidy model? Like what's the relationship?
Okay, so I repeat the question. The question was, how does ML3 compare with Tidy models? So the main differences are we use R6, data table, and future for the basic course. This is not used in the Tidy models framework. They use a different syntax, and other than that, they also have more or less the same approach. So they have specific sub-packages for learners, for tuning methods, for resampling methods. Their syntax is more aligned with the tidyverse syntax. You've seen our syntax is a bit different. And you can do benchmarks here and there and compare things, but in the end, I think when it comes to large data and going nuts with ensembles and other things, even though this has also been implemented meanwhile in Tidy models, you have a lot of freedom space in Ml3, but it's hard to keep up with recent developments in both frameworks. So sometimes one framework might be easier or might provide something that is not available in the other, but then the other catches up. So it's essentially your choice. So there's not much communication, unfortunately, between the developers of both. So we both do our thing, so to say, but you should most likely be able to do anything in each framework. So recently, they also added support for spatial resampling methods in the tidyverse that was for a long time only available in Ml3, but now also there. So I would say just check out both, make your decision. We are not angry if you use another framework than ours. You know, we just want to make things easier. If there's other things that you use, fair enough. So that's more or less what I can say about this. More questions? All right, then let's do some hands-on. So all of this code is all, if you just use this code, you can just check that out and open the project and should get you going. And I'll click through here a bit and we'll see and explain a bit on the side.
Just one quick question.
Yeah.
I see you're using RN.
Yeah.
And how do you initiate the? I think the packages are already pre-installed, right?
Yeah. So if you open the project in the working directory of the hands-on package and click just on this R project, it will try to initialize RN and eventually already restore the packages or ask you, and you should just restore them, and then you have all the packages needed to rerun this.
Okay, so there's not much you should do. Should someone work automatically?
Yeah, or just in case, just call RN restore, and then it should work. There are instructions in the README as well. All right, so I'll load the Ml3 verse and the Ranger package, because that's for the learner we want to use later on. Here I use the data from the empty cars, and we create a task here. And remember, a task is just a wrapper around the data set with specific metadata information. So we can, for example, query, look at the task in the first place. We see that we have the target specified, some properties, if there would be any, and we see we have 10 features. That we can again query the feature name specifically, or also check the target name or some other names. So there are more fields in the task that you can just access. So these are fields of the R6 objects, and the train function would be a method, for example. Then we create a learner. In this case, we use a random forest. We say, okay, it's a regression task, so we want to use a regression learner. And we also have a look at how a learner looks like. So we see we have a learner regression ranger object here. We see that there has been some default change by Ml3, meaning that num threads to disable the internal parallelization. We see what packages it requires to run, right? So we need Ml3 core, the learners, and of course, the actual upstream package. We see what predict types are supported, what feature types are supported, and properties means, for example, we can do feature importance internally with the learner. We can do a hot start backward tuning. It supports different feature weights that we could potentially specify, and this differs for each learner. But you get an overview here of what the learner is capable to do.
So, Patrick, so now, for example, you want to change the number of threads to all.
Yeah.
How would you do that?
You said, so for example, you could learn a random forest, and then you do param set, and then values, and you have here set and get values, and you would just set values and change this value with replace it, and it's being changed in place because of the way R6 objects work. So you have always a setter and a getter in the objects, and you can set and change values and just retrieve them. So that's how you would do it.
But how would you change it out to all cores?
All cores. So here, I think, I'm not sure about the correct, so I need a list. I think I can do it like this. Let's see if it works out of the box. I usually don't do it like this. All cores, I would probably use Parallelly. If that is installed, I don't think, available cores, maybe this works. No, must have names. Okay, so what did I do wrong? I don't know if I need to use it like this or a list or a vector. I think maybe that's it. Could be. Let's see. Where do we have it? We can also query it. Oh yeah, now we've changed it.
Okay.
Because parallel num threads, as we did it here, always queries.
The first time you wanted to make a list and that didn't work. Now without the list, it works.
Yeah. So
these are these little things that frustrate.
Yeah, but so these sometimes differ, but usually we want to operate on vectors, not on lists. But so I think I'm not sure I just use a vector. So if I do it like this, it didn't work. But I would have to look it up so it didn't work like this. So, but you really just have to do it like this, and then just probably comma notation for other parameters. But this is how you would do it and how you would change values in place. And here for example, if you would query the model, of course we get null because we haven't trained any model yet, right? So, but after we tuned and trained the model, this slot would be filled. Yeah.
With the set value method, how do you look up documentation for that? Like in Python, if you do a question mark and you have like an object and a method, it will look up.
Yeah, here it's also question mark. You can do it, but you need to specify the class that we operate on. For example, we can have a look at the class, right? It's learner regression ranger or learner, which inherits from learner regression or learner. But actually, you can, for example, use this class, and then you get the help page here. And here, there you have all the specifications for all the methods, for all the classes, and you see all the inherited methods. And for example, if we would look for param set, right? We would get the documentation here, and then there's a link that we could go to the param set documentation, and here you have again more documentation of that. So this is how you would do it. So keep in mind that this is using inheritance here, right? So this is the stack. So the top class is the learner. The learner inherits everything to learner regression, and learner regression inherits everything to or passes over everything to learner regression reinsurance, of course. So then 1 minute left. Let's maybe tackle this and then we have a break.
We can go in overtime just if you want to finish it. So.
Yeah, well, we have some. I have the second block as well. So, but maybe let's talk about the tuning, or maybe let's see how it goes. So we use the tuning spaces package here, which is a package that gives us some default tuning ranges for specific learners. For so LTS means load tuning space, and we've created now a ranger with the default tuning ranges of the tuning spaces packages. And if we have a look here and print this object, we see the tuning space defined for this learner. So we tune Mtri ratio between 0 and 1. We tune the sample fraction. We tune num3s. We don't optimize replace. I think this is just set to a fixed value because it's an A here. And the tuning, so this object, the tuning space learner, has actually the learner included into a field. So we can, for example, create the learner here and then also the other model at the end, which would be in the learner slot after we've trained the learner. So this is more like similar to an auto tuner that we've created before. It wraps a learner, and by wrapping a learner, it adds a tuning space by default. But it doesn't yet add a tuning method, right? This is different here. So to tune all of that, we cannot use the tuning space learner, but we need to query the learner first, which has now our parameter set here in the parameters listed. So you see, compared to the first one, we now have all of the tuning space here in so-called tune tokens, which means they're automatically optimized in the learner. So this is similar to an auto tuner, but a bit different. And we can use this learner now by specifying a resample method here. For example, cross-validation. We look at the object. We, of course, need to define a measure, right? In this case, we use the RMSE, the root mean square error, because we have a regression use case. And am I still here? Exactly. And to trigger all of this, we use the tune function. What the tune function needs, it needs a method, a tuning method, in this case, random search. We say we want to use the empty car stars. We want to use our learner random forest that has an included tune token parameter set that is being optimized on. We pass the resampling strategy. We pass the measure, and last but not least, we pass how often should the tuning iterate over this tuning space. So in this case, we say, please iterate, try out 20 different settings of the tuning space in a random search manner. And then we trigger it, and you see all the output. This is the default from a logger package. If it has finished, we can have a look how it looks like. So usually you see that it's something like this: applies learner on task cars, and then it prints you the iteration of this. And BBOTK is the internal tuning package that at some point gives out the results of the tuning iteration, which most often you're not interested in. You're interested in the final result. But
And can you turn off all the output?
yes, with the next slide.
Right.
So you can set different logging thresholds here. If this is info here, if you set it to warn, you don't get all the info calls. You just get some warnings. This needs to be done for the Ml3 logger and for the BBOTK logger, which is, you see here, this is the BBOTK logger. So this always means the logger type, and this is the logger level here, the info. So we turn this off, and in this case, we turn it off because we want to use a progress R. We want to have a progress bar, and we run the same again, and now we get a progress bar, and no log output anymore.
Cool.
we can look at the tuning instance, and here in the tuning instance, we see all the results from the tuning. We see the final result, so the best result that has been tested over all instances. We see the search space that has been tested on. We see the tuning archive, which means all the settings that have been tested. We see it's exactly 20 because we said term equals 20. And yeah, that's what I wanted to show here. We see that we can query the optimal parameters here with the by querying the result learner param-vals slot. And finally, we can also, well, that's unfortunate. So let's install the package. We can also plot the final tuning instance and get an overview of how the tuning went and where the specific settings, what they yielded for different.
I would have just expected a curve showing where's the minimum or something.
There are different ways to visualize this. I think we have a curve of implemented in some ways, but I cannot, I don't know it out of the box. But yeah, there are different ways to visualize the tuning in the end, and you can also build your own stuff from the archive. So there's also a way to list all the tuning methods as a data table objects. So instead of just using the tuners. And finally, we are almost through. We can now say, okay, we have optimized some. So we have these optimal hyperparameters here in this slot. We set these for the parent set values of our actual learners, right? So this is what you usually want to do. You tune, you apply the best config to your learner. Then you train the learner again on the final complete data. And then here, the last step would be to predict on some new data, which I don't have here right now. But this would be, if you recall, on this block I showed you from these two worlds, the full left side of this block that we covered. Learner, task, tuning, applying the best parameters to your learner, training on the full task, doing a prediction. That's what we did here. And now we are a bit over time. I think it's good for a break, and then we continue with the second part.
Let's stop the broadcast. Thank you so much. Let's have a break, coffee break. Come back.